Everybody for coming. So we're about to start this great session about optimization on manifolds. So our first speaker is Jérôme Stenger that represents this work on canonical moments for optimal uncertainty quantification on a variety. Thank you.
Thank you for the introduction. So I'm going to present my PhD work that is supervised by Fabrice Gamboa, here present. So this is going to talk about canonical moments for optimal uncertainty quantification on a variety. So first, let me introduce what is optimal uncertainty quantification. So what is the basis? So we have a model here. The model is a computer code that can be seen as a black box function. And the inputs of the code are modeled, are physical parameters. They are uncertain, and so we model the inputs as random variables. Okay? So for each input, we associate a probability distribution, and we propagate the uncertainty on the input through the model so that the output is also a random variable. So we are interested in some quantity of interest on the outputs. So this could be a quantile, a probability of failure, as in the example here, or any kind of quantity of interest. The thing is, the choice we make for the probability density is also uncertain. Okay? And if we change the density we have chosen for every input, we also change the output distribution. And if we change the output distribution, we change our quantity of interest. So we'd like to be more robust. We'd like to be to quantify the uncertainty we have on the choice of the input distribution. So what we do, we'd like to compute the worst case. So we take a set of possible input distribution. We take a set of measures, and we like to compute the worst case. So this is the maximal probability of failure, or the maximal quantity of interest. So the problem can be written this way. We have a quantity of interest, phi, that is a function of the input distribution. So this is a function of a measure. So for instance, if we compute a probability of failure, this is written this way. So this is a function of the measure. This computes the probability of failure. And we can see that this function is actually a linear function of the measure. So this is quite simple in this situation. And we take a set of possible input distribution, and we like to compute the maximal, the optimum of the quantity of interest over this set of possible input distribution. So we are not going to take all possible probability measure because the space is really big. So we are going to enforce constraints on every input. So this is called a moment class because we enforce moments for every on the input distribution. So for instance, for every parameters, we enforce the mean, we enforce the variance, and so on. So this is just moment constraint. So this is the shape of this space. Every input is associated to a measure nu I, okay, and we have a tensorial product because we consider that every input is independent. And on each input, we enforce just moment constraint, okay? So this is called the moment class, and we are trying to optimize our quantity of interest over this moment class. So this space is non-parametric as in an infinite, so the optimization at first glance is quite hard. Fortunately, we have a reduction theorem that I'm going to present right now. So we are going to say that, our quantity of interest is a quasi-convex function. So this is an assumption we make. So a quasi-convex function is a function that satisfies this inequality. Okay, so on the left is just a convex function, and on the right is a quasi-convex function. So this is a way bigger class that includes the convex function. And the thing is, if we are on a compact set, so on the real line, if we are on the segment AB, the maximum of a convex function is reached on the extreme point. So this is either A, either B. So this is really simple. And for quasi-convex function, this remains true. So for a quasi-convex function, the maximum is reached on the extreme point, either A, either B. So this is simple because this is the real line, but actually it stays true on arbitrary space, on a more abstract space. So we have a space of measure, the moment class, okay? And the space of measure is suppose compact and convex. It is compact and convex. And our quantity of interest is a quasi-convex lower semi-continuous function. And so that's the supremum of our quantity of interest over this space is also reached on the extreme points of the space. So right now, the only thing we need to do is to characterize the extreme points of a set of measure. So the question, well, is what are the extreme points of the moment class in our case? And I'm going to give you the answer right now. So this is a simplified moment class, okay? So you take a distribution, a probability measure, okay? And you enforce moment constraint, okay? And the extreme points of this set are discrete measure. And we know the cardinal of the support because these are discrete measures supported on at most n+1 points. If we have n moment constraint, the extreme points are supported on at most n+1 point. So this greatly simplifies the problem. But first, I will try to show you where does this come from with a simple example. So take 1 kilo of sand, okay, and you like to arrange the sand so that you maximize the mass of sand on the red region here. You like to keep the seesaw balance, of course. So what is the mathematical equivalent here? You have a probability measure, mass 1. You'd like to maximize the probability to be on the red region, and you have one constraint on the mean because you want the probability measure to have a mean equals to 0. Okay. And so this is the kind of problem that we are dealing with. So how do you proceed in this example? Well, you need to reduce the arm lever on the right side. So you put as much mass as you can on x equal a. And on the other side, you do the same, but you maximize the arm lever so that you put as much mass as much sand as you can on the extremum here. So your optimal probability distribution here is a discrete measure supported on 2 Dirac masses. So you had one constraint on the mean, and you see that the optimum is a discrete measure supported on at most 2 Dirac masses. So in our case, we optimize probability of failure or any quantity of interest. So the supremum of the probability of failure can be written this way. And here, every input is discrete now. So that to compute in order to compute this probability, you just need to compute, well, you just need to call your code on some grid, d-dimensional grid, okay? And you see now that the problem is parameterized because the whole optimization only depends on the weights and the positions of the discrete measure. We were on a set of probability measure that was non-parametric, and now we have a parameterization with discrete measure. And this can be even more simplified because, as I said, we have n constraint, n moment constraint. So we have a set of equations that corresponds to the weights and the position. So the first equation is the sum of weights equal 1, of course, because this is a probability measure. And the other equations are the constraint on the moment. So the first one is the mean of the measure equals C1, the second moment, and so on, just, until the nth moment equals to Cn. And you see that this is a von der Mondt system that is uniquely solved. So if you know the position in the system, if you know the position, you also know the weight. So the whole parameterization only depends on the position of the discrete measure. Of course, this system is not easy to solve because you need to ensure that your weights corresponds to a probability measure. So the position cannot be taken arbitrarily. Let's take an example. If you take a measure on 0.1 with 2 constraints, the mean equals to 0.5 and the second moment to 0.3. You have 2 constraints, so you're looking for a measure supporting on at most 3 points, okay? And you can see that you cannot choose arbitrarily the position because sometimes it gives you weights that does not correspond to a probability measure. So the whole optimization is realized over this space. And why this space is a manifold? Because, well, the parameterization is only depends on the position. So we are actually optimizing in this example on a cube. Okay, and we need to ensure that we need to maximize our quantity of interest over this manifold. The thing is, the more constraints we had, the more the volume of this manifold is small. And actually, we can show that it's reduced quite quickly to 0. So the optimization in high dimension is quite hard. And so we'd like to reparameterize this manifold so that we do not, we simplify the optimization process. So to do this, well, we proposed a new parameterization based on canonical moments, and this is what I'm going to present right now. So what is the problem with this manifold? The thing is we have moment constraint. And moments are not easy to work with. Why? Well, here I have a uniform in 0, 1, uniform distribution in 0, 1. This is the sequence of moments. And here is a uniform distribution in 0, 2, and this is its sequence of moments. And you can see that basically moments there's no relation between the moments of a measure and the structure of the distribution. So the idea of canonical moments is to normalize the moments of a measure. So how does it work? Well, take any distribution in any probability measure in 0, 1, okay? And you take its sequence of moments. And you put it on a graphical representation. So here, for example, this is the first two moments, first moment, second moment. And you can see that the moment of a measure cannot be whatever, okay? And for instance, if you look at all the measures that have mean equals to C1, well, you can see that the second moment cannot go above C1 and cannot go below C1 squared. So basically, if you take a distribution and you look at the second moment, well, you know that the second moment of any distribution here is between these two bounds. So the idea of canonical moments, well, is to normalize the moments. So how do you proceed? Well, you take the moment of order n, and you minimize, and you subtract the lowest value this moment could be, divided by the ratio of the maximal and the minimal value it could be. So this is called the canonical moments, and with this transformation, all canonical moments belongs to 0, 1. This is quite easy to catch. And moreover, with this transformation, we are invariant by affine transformation. So for instance, any uniform distribution in AB have the same canonical moments. And you can feel this way that the canonical moments are deeply related to the structure of a distribution. So this is what we used because we can link the canonical moments to the support points of a discrete measure. And as I said before, the parameterization relied on the support points, the position of the discrete measure. So I'm going to show you how we link the support position of the discrete measure to the canonical moments. It's quite easy. We define these polynomials, okay, and the roots of these polynomials are the support points of the discrete measure. Well, we can show that these polynomials can also be expressed, I mean, its coefficient can be expressed with a sequence of canonical moments. So we have two ways of defining the same polynomials. One relies on canonical moments, and the other on support points of the discrete measure. So our manifold was, well, the sequence of position of discrete measure, okay? And we have shown that this sequence of position corresponds to the roots of these polynomials. So actually, this means that the manifold is an algebraic variety because it means it is the zero locus of this set of polynomials, well defined by with canonical moments. So we have found the structure of the manifold, and it allows a quite simple optimization. So in practice, how do we proceed? Well, take another example. So you take any probability measure with n constraint, n moment constraint, okay? So you are looking for discrete measure on at most n plus 1 points, okay? As I said, through the position, you can define the polynomials that can also be defined with a sequence of canonical moments. So in practice, what do we do? Well, the first n canonical moments are set. We have n moment constraints. This is equivalent to n canonical moment constraint. So the first n are always set. But the n plus 1 left are free parameters. And they all belong in 0, 1. So how do we do to explore the manifold? Well, it's quite easy. We generate a sequence in 0, 1 power n plus 1. Okay. Each time we have a sequence of canonical moments that defines a polynomial. And to get the position of the discrete measure, we just need to compute the roots of the polynomials. So the whole manifold is only parameterized now with in n 0, 1 power n plus 1. And we do not have any constraint because each time it corresponds to a measure discrete that satisfies the moment. So this is the previous example. So here it was the measure in 0, 1 with mean equals to 0.5 and second moment to 0.3. And this is the shape of the manifold we can get. So here, how do you read this? Well, each point here, the coordinates of each point, the 3 coordinates, corresponds to the 3 positions of a discrete measure that satisfies this constraint. Okay? And if we want to minimize our probability of failure on this manifold, you just need to, well, to find the global minimum over this set, and you have a free of constraint optimization because everything is parameterized in 0, 1 in the cube. So this is the kind of algorithm we get, and some references. Thank you for your attention. I'm done.
Okay, so we have time for a few questions. Yes?
The problem you're describing reminds me of experimental design. There also you have to choose measures.
Yep.
And but you're trying usually to minimize the functional. But
yep.
Of course, if you multiply this with -1, you get a functional to maximize.
Yeah, we thought of that.
Something to do with.
The problem of optimal design is that you try to minimize your quasi-convex function and not maximize it. So you cannot, the solution is not found on the extreme points. So this whole theory cannot really apply.
But often there also you get measures which are supported at few points. Why is that?
Oh, well, in optimal design, you choose discrete measure usually.
Maybe we discuss this later.
Oh yeah, okay, sure.
Any other question? Okay, maybe I have a little one. So what is the effective or standard size of number of constraints that you have?
Usually, so this methodology, we applied it on a code that takes, well, a 10-dimensional code. So we have 10 inputs, and we put 2 constraints on each input. So each input is supported on 3 Dirac masses. So the total dimension at the end is 30, something like this.
And computing the roots is...
Yes, it's easy because if you have 2 constraints, the polynomial degree is only 3. So if you have 2 constraints, you're looking for measure on supported on 3 points. So the degree of this polynomial is 3. So you just need to compute 3 roots each time. So it's quite fast.
We are on time, so let's thank our speaker again.